dynamical system, it looks something like this. For I equal to 1 to n, the total number of particles. So if we assume that the system is actually consisting of n number of mass particles, and there the principle of virtual work was like this: in I, AI minus Fi, the force acting on it, dot delta Ri, this is equal to 0, where delta Ri is the virtual displacement. And this delta Ri, because this is a virtual displacement of Ri is the virtual displacement of the ith particle, and we know that all the coordinates Ri can be expressed in terms of lesser number of generalized coordinate. Lesser because there may be many constraints which these particles need to satisfy during motion, and that will reduce the number of independent requirement of number of independent variables to describe this motion. So if we have m number of independent variables, that is independent generalized coordinate, then one can write down this as delta. So d delta Ri, this is equal to delta Ri del Qj and delta Qj, where j is from 1 to m. Okay, so there are m number of, or let me write down small m, just be consistent with the previous class. So delta Qa j's are the virtual displacement of the generalized coordinate. So this generalized virtual displacement one can roughly say. So if you substitute this expression here in the previous expression and then rearrange the terms, I have shown you, well I did not derive, but I told that this can be written something like this: j equal to 1 to n, okay, and then this was d dt of del t del qj dot minus del t del qj minus qj del qj, this is equal to 0, where T is the total kinetic energy of the system. That means this is equal to half mi vi square, I equal to 1 to capital N, total number of particles, this is the total kinetic energy, and one can write down in terms of vectors, this is half I equal to 1 to n, then mi, so vi dot vi, that means, well, so vi dot vi. So this is the total kinetic energy, and Qj, this term I named this as the generalized force. And this was equal to delta Ri this was delta Ri delta Qj. This is I equal to 1 to n, and this was Fi delta I. So therefore, this was Fi dot delta Ri delta Qj. So this is the expression of the generalized coordinate.
Sir,
Generalized force, yes.
sir, what is that written? That summation of mi bracket under v?
Vi dot Vi. This is dot product of Vi with the Vi itself. So this is the magnitude Vi square, which is nothing but the dot product of the two vectors, same vector, right? Identical.
Okay,
Vectors.
sir, okay.
This will be useful because in mechanical systems we can express the vectors. Normally we express the vectors, velocity, etc. in terms of vectors. So maybe this notation will be more useful, this particular notation, because directly we can work with the vector here as shown in this particular case. Okay, so but this is nothing but the same thing, vi square, which is nothing but dot product of two vectors, the same vector, vi dot vi, which is nothing but vi square. Now these particular, from this result actually we argued, so these were all written in the last class, right? So this is not new. So I am erasing this part, and then we said that if this is true for any arbitrary combination of delta qj, so delta qj's are arbitrarily chosen, they can be anything, and for any arbitrary value of delta qj, this is true. So then this is only possible when this part that is within the curly bracket, this becomes identically 0. Okay, so from this, if this is true for all delta qj's which are arbitrary, so this can happen only if this condition is satisfied. Delta q, this is j dot minus del t del qj is equal to q j, or j equal to 1 to n. So these n conditions are to be satisfied, and then this will be automatically satisfied. And these equations, I told that this is Lagrangian equation because Lagrange first derived this, but later on there are some modifications I will tell. Now QGs, now this is the generalized force. Now there are some forces, two kinds of forces are there. These are all because of the external force. Remember that in this particular way of writing the equation of this particular deriving these equations, what we have done, what is our advantage? There are all constraint forces. Many constraint forces were there because there are many constraints, but all these constraint forces are now vanished because there is no trace of constraint force here. Only thing, the force appears in these QJs, and these are the external forces. So external forces we cannot eliminate. So external forces will be there, but by way of writing the equations in this particular form, the constraint forces are now eliminated. And remember that these constraint forces are very difficult to derive. I'll give you an example definitely to show that how effective this particular equations, this method is. So QJ now.
Sir,
Yeah.
sir, can you please explain that equation where qj is equal to summation fi for generalized force?
This is Fi on the ith particle. Suppose if I the external force, total external force, is dot delta Ri delta Q J. So this is the generalized force, expression for the generalized force. Okay. Now we'll have two kinds of force. One kind of force. Now, how many kinds of force are there?
So why I didn't understand why that equation is like that.
Why this equation is like that means this Q are Qj.
Sir,
Which equation you are talking of?
the q equation, the qj.
No, that is because what was Qj? Qj was, so in that particular, in this particular, in the derivation I had Fi dot delta Ri. Okay, I equal to 1 to n. And delta Ri, I wrote that this is nothing but I equal to 1 to n Fi dot, this one delta Ri was delta Ri delta Qj delta Q j equal to 1 to n. So what I did, I interchanged the summation sign, and this becomes equal to j equal to 1 to n, then I equal to 1 to capital N Fi dot delta Ri delta Qj and delta Qj. So this particular term, I consider this as Qj. This came in the equation of motion. In the derivation of the, from the virtual work principle, this term appeared. If you look back at the virtual work principle, and if I got delta Ri was there, and from that equation, I got this expression. Okay, and this particular summation I named. So this is the Qj and delta Qj equal to 1 to n. So this is the naming of this particular expression. Okay. And I call this
Okay.
term. So this is Qj. Okay. Now, how many types of force? How many types of forces are there in mechanical system? Mechanical system, you can say. There are two types of force. Can you name the types of force?
Conservative and
Right.
non-conservative.
There are forces which are conservative and which are non-conservative. That means the conservative forces are the forces which are obtained from the potential energy. Say, when I say a force is conservative, that means Fi, this is a conservative force, when this is actually obtained from one function. So let me not write down. Say force is conservative when this is obtained from a function, potential energy function. That means what it means that Fx equal to minus del u del x, Fy equal to minus del u del y, and Fz equal to minus del u del z. So if we are able to write down the forces in this particular form, where u is a function of x and x, y, z, then this is known as the conservative force. And if we are not able to write down the force in this particular form, then this is non-conservative force. The difference between the conservative force and the non-conservative force is that if this force acts on the particle and the particle comes back its own position after some time, then the total work done by a conservative force vanishes. Whereas for the non-conservative force, it does not vanish. So it becomes some substantial quantity for non-conservative force, where if you consider that cycle, this F dot delta R, this becomes actually 0 for conservative force. And for non-conservative force, this is not equal to 0. Now, if you allow me to write down the forces, let us say Fi, ith force, that is force on the ith particle. This is actually a derivable in the function from u, which is now can take any value x1, x2 up to xn, y1, y2, yn, similarly z1, z2. U is a function of those quantities. So if Fi, so this means that Fi, this will be equal to minus Fi, the x component of this Fix will be this one xi, Fiy, this will be minus del u del yi, and Fiz component, this will be minus del u del zi. So if the force is like that, then of course our generalized force Qj, if this is so, Qj will be equal to I equal to 1 to n, then Fi dot del Ri del Qj. Fi is in this particular form, so this one becomes I equal to 1 to n gradient of Q with respect to Ri dot delta Ri delta Q J. So this means actually if you expand, this becomes delta U del x1 del Qj plus delta U del y1 del Qj plus delta U del z1 del Qj, delta U del x2 del Qj, delta U del y2 del Qj, and so on. So if you expand this, you will be able to establish very easily that this expression is nothing but del U del Qj. Del U del Qj. So this is the expression one can get very easily using the fact that Fi's are actually derivable from potential energy. So if you have conservative force field, then Qj is expressed as minus del U del Qj. Is this clear? I suggest that you expand this and see yourself that whether you are able to get this expression or not. Okay.
Sir,
Yeah.
So, can you explain why did you write an Ri below delta?
All right.
Del
Oh, that
of
is because I am taking the derivative with respect, so for the ith particle, I am taking the derivative with respect to del x1, del x, del x1, del y1, del z1. Okay. Because normally here, uh, so maybe here what you'll say that maybe it's better to write down this one. That is, I am taking the derivative for the ith particle. I am taking the derivative with respect to xi, yi, and zi. Suppose there are n particles, so force will be function of x1, x2, x3, xn, all this stuff. Now the ith particle, the force is actually derivable from the position of the ith particle. That means in the differentiation only the xi will appear, xi, yi, zi will appear. So this is a kind of a notation. What I mean is that Fix, this is what is the expanded form. Fix will be equal to del u del xi. It's not, there's a subscript I with the, on x, y, and z. So therefore, I'll have to have some kind of notation, some subscript or some form of notation to denote that the differentiation with respect to xi, yi, and z. Okay.
Okay, sir.
Okay. Good. So if qj equal to minus del u del qj in this particular form, then what happens to our equation of motion? The equation of motion. So now you see that ddt, we have the n equations, del t, del qj dot, minus del t, del qj, and this is qj. Qj is equal to minus del u del qj, right? And u is a function of only x1, x2, x3, so therefore it is not a function of del qj, so I can write down del u del qj dot equal to 0 because u is a function of only ri, so that means u is a function of ri, r. So u is a function of ultimately qj's, right? Not qj dot. It does not. This potential energy depends only on the position, not on the velocity of the particle. So del u del qj j dot will be equal to 0. Now, if you take this into account, then you can write down this expression very well. That is, this becomes equal to ddt of del t minus q del qj dot minus del t minus q del qj, and that is equal to 0. Right? Is this clear? This part actually becomes 0 because del u del qj dot is 0. But this actually, when you transfer to the left hand side, it becomes positive, and that's why you have t minus u del qj. Fine? Clear? Any doubt?
No, sir.
Okay, sir.
Good. Now, what we name in this function, kinetic energy minus potential energy, this is actually a function of qi, qi dot, and that may be a function of time explicitly also. This is known as the Lagrangian of the system. This is the Lagrangian function, or the Lagrangian of the system. This is the Lagrangian. Okay, so if t minus u is defined as the Lagrangian, then the equation of motion for the conservative system, this becomes equal to ddt of del L del qj dot minus del L del qj. This is equal to 0 for j equal to 1 to small n. Okay, so in books, normally this is called the Lagrange equation motion because it contains Lagrangian. But you see, the Lagrange derived this equation with the kinetic energy, and later on, well, of course, in this the same work, he derived this equation also, t minus u. And to honor the discoverer of this equation, we name it Lagrangian functions. Okay, so this is the Lagrangian, and this is valid for if only if the forces are conservative. Okay, if the forces are conservative and non-conservative both, That means F has certain conservative component and certain non-conservative component. So for the conservative component, this becomes equal to minus delta, this is RIU plus FI NC, non-conservative part. For the conservative part, of course, since it is linear with respect to Fi, so therefore, for the conservative part, we'll consider this total potential energy and it will be like that. And for the non-conservative part, we'll have here on the right hand side, this is Qj, and maybe this we call Qnj NC, that is to say that this potential energy or this generalized force is due to the non-conservative component of the force. So the conservative component will be taken inside the Lagrange equation as the Lagrangian, and the non-conservative force, of course, it cannot be expressed in any of the form, so it will be lying outside. So this will be the general form of the equation of motion. This part is understood?
Yes, sir.
Okay, good. So we will consider henceforth the Lagrangian equation like this. If you have non-conservative force, then this part right hand side will be non-zero. If it is conservative system, then the right hand side will be 0. So there are n equations which will describe the evolution of the system at any particular time. Given the initial condition, these equations need to be solved to find out the value of Qj's at any particular time. Okay. Now let me tell you how this equation becomes useful. Why are we learning this thing at details? So have you all noted down this equation? This is very important, and I suggest that all of you at least, commit to your memory. Okay, so you memorize this for this equation. This is a very important equation in mechanical engineering, in the dynamics. Okay. So Lagrange equation. Okay. If you have a simple system like this, of course, you cannot understand the advantage of this Lagrange equation. Suppose you have a single pendulum. Okay. So how do you derive the equation of motion? There are ways to derive the equation of motion using Newton's method. That means using drawing the free body diagram, drawing all the forces, mg, and this force T, the constant force. This constant force we'll have to take, and then we write down mass times acceleration. This is equal to the net force. That means if we consider this x and y coordinate, then this will be equal to mg I, and this minus this plus t. So if you expand, then you'll get m, where a is the m times a is nothing but L theta double dot E theta, where this is the E theta and this is ER, minus L theta dot square ER. This is the acceleration, and this becomes equal to T, which is equal to minus TER plus MGI. I is nothing but ER cosine theta minus E theta sine theta. So if you equate the vector wise, if you equate, then you get two equations: m L theta double dot minus mg sine theta. This one expression you get, and minus ml theta dot square equal to minus t plus mg cosine theta. So here these two equations are obtained, of which only the first equation ml theta double dot minus equal to minus mg sine theta. This is the only equation which is required by us. Other equation, what it does, it gives the value of the t. There is the, once you solve this, you get theta as a function of time. Then from here, from the second equation, you get the value of the tension, string tension. So the second equation is not useful to us. But in Newton's law, we'll have to actually work with this equation. We get this equation because we have to consider all the forces. Okay, T we have to consider because otherwise we cannot write down the equation of motion using the Newton's laws of motion. Okay, mass times acceleration is the net force acting. Understood? So this is very simple to derive, and I hope that all of you should be able to do that on your own. But if you consider the Lagrange equation, then it is easy to see because now the kinetic energy, this is, let us say, T star, just to name that this is the kinetic energy. Kinetic energy, this becomes equal to half mv square. So half m, what is v? V square. V is nothing but r or L theta dot E theta. So V square will be equal to V dot V equal to L square theta dot square E theta dot E theta, which is equal to V square L dot square. So V square will be L square dot theta dot square. So this will be half m L square theta dot square. So this will be the kinetic energy. Potential energy, if you consider this to be the reference point, then the potential energy will be L. This will be equal to minus L cosine theta times mg. So this will be the potential energy expression. Okay, if you assume that this to be the reference. Okay, so the potential energy will go down. This is not going down, but anyway, potential energy is like that. Minus. So potential energy will be smaller if you go towards the earth. So that is what we have. So from this, it is easy to find out the expression for the Lagrangian. Lagrangian will be T star minus U. This is equal to half m L square theta dot square plus L cosine theta times mg. Okay. And then we'll have to take this derivative, that is del L del Qj. That means Qj dot, we'll have to take. That means here del L del theta dot, which is equal to m L square theta dot, and del L del theta, which will be equal to minus L mg sine theta, right? So now the equation of motion will be d dt of this quantity del L del Qj dot, which is equal to m L square theta dot minus del L del theta, that means minus mgl sine theta. This is equal to 0 because there is no non-conservative force present in this particular problem. If you rearrange this term, if you take the derivative, it becomes very simple. ml square theta double dot plus mgl sine theta. This is equal to 0. Once again, we get this equation L theta double dot plus d by L sine theta equal to 0. This is our equation of motion. Note that here I have to work only with one particular equation, with one equation only, and the other part, that is T, the string tension, disappeared in this formulation. If you want to find out the string tension, again, of course, we'll have to go back to Newton's equation to find out the string tension. But here, for finding out the configuration of the system, we do not require the value of the string tension. Okay, the string tension, which is actually a constant force, this is not required in this particular formulation. So in some way, this is a little advantage. Of course, this advantage is not very clear from this particular problem, because this problem is too simple. But if you consider a little bit more complicated problem, then you will see how the Lagrangian formulation, it helps us. suppose I have a double pendulum. So now we'll consider a single pendulum. I consider a single pendulum. Now I will consider a double pendulum here. Okay. We consider a double pendulum. Now, if you want to write down the equation of motion using Newton's law or in force equation, you have to draw the free body diagram of both the particles. Here, it will be T1, and this will be T2. This will be M1G, and for this particle, this will be T2 and M2G. That's what we said. Now, well, then if θ1 and θ2 are the two variables, then the equation of motion for the first mass will be equal to m1 L1, suppose this is L1 and that is L2, L1 θ1 double dot E θ1. I consider this two unit vectors. This is ER1 in this direction and E θ1 in the other direction. And similarly here, I consider let us say some vector, maybe E θ2 and ER2 and E θ2. So these are two vectors I denote. So M1 L1 θ1 double dot minus L θ1 dot square ER1. This is equal to T1 plus T2. Okay. T1 plus T2, that is what we have. And what is T1? T1 will be equal to again the same thing. Okay, let me write down this is the first equation. The second equation, you will get M2. And what is the acceleration of this point? What will be the acceleration of this point? Mass particle M2. How to get the acceleration? How to get the acceleration?
The acceleration of M1 plus relative acceleration between those two.
No, what will be the acceleration of M2? How to write down?
By using a generalized variable.
Yeah?
A generalized variable.
No, not generalized. Yeah, generalized variable fine, but how to represent in this vector form the acceleration of mass H2?
Sir, at the acceleration of mass relative.
Okay, so let us say acceleration of M1 plus the relative acceleration of this with respect to this mass. Okay, the first mass. And here, this relative acceleration, this will be equal to minus L2 θ2 dot square ER2, because if you consider this the coordinate, then this is the ER2, okay, and this plus L θ2 double dot E θ2. Okay, so that is for the acceleration of this mass. Where A1 will be equal to, shortage of board, you can, okay, I can go further. But A1 equal to here L1 θ1 double dot ER1, E θ1 minus L θ1 L1 θ1 square E1. So it's a complicated expression. So it's the acceleration of this mass plus the acceleration of this mass with respect to the first mass. Okay, and this acceleration, as if this point is actually fixed and this is rotating, is having a pendulous motion. Okay, so this is what the acceleration of this mass will be. And then T1 and T2 here. So this is well, let me not write down this. So this will be equal to, well, here we have this plus mg m1 gi. Okay. So this will have minus T2 because T1 is in this, T2 I took positive in this direction, so therefore T2 on the particle M2 will be minus T2, and this is plus M2G. So these are the two equations which we will have to solve. Solve means that I'll have to find out there are two vector equations, four equations, T1 and T2. First of all, I have to write down, express T1 and T2 in terms of the theta1 and theta2. T1 is very easy to see. T1, the direction vector will be E theta1, nothing else. But for the T2, it will be, well, T2 is also not very difficult because T2, the direction is in the direction of E theta2. Again, you'll have to replace this E theta2 and ER2 in terms of this theta1 and theta2. So it is actually, you may try to get the equation of motion. You will get four equations. Why four equations? Because in this equation, you will get this equation will involve the magnitudes of the string tensions. T1 and T2 will be there, which is of course not required for finding out the motion of the system. Okay, so we could dispense with, but using Newton's law, this is not possible. If you use Lagrange method, I ask you to derive the equation of motion using this particular expressions, the Newton's laws. Okay, please do it conveniently. If you have, if you use Lagrange equation, then it becomes a little simpler. Why should I say a little simpler? It actually simplifies a lot. So here you have, this is theta1 and this is theta2, m1 and m2. So our kinetic energy expression T, what I need is the kinetic energy. Kinetic energy of the first mass, this is half m1 v1 square plus half m2 v2 square. Okay. So kinetic energy of v1, so v1 will be v1 square will be equal to v1 dot v1, and this, because it is moving only, it is like a circular motion, so therefore this will be L1 square theta1 dot square v1 square. What will be v2? v2 square? v2 square you can find out, but it will be easy to obtain v2 as a vector first, the velocity vector. Velocity vector will be equal to velocity v1, and the relative velocity, you see that relative velocity will be, if you consider this is ER and E theta here, then the relative velocity will be, again, R2 and E theta 2 I will consider, so relative velocity will be equal to R L2 theta 2 dot E theta 2, okay, E theta 2. So that is the one. And what is V1? V1 as a velocity, this will be L1 theta 1 dot E theta 1, right? E theta 1. And this plus L2 theta 2 dot theta 2. So if you take, so this is V2. So V2 dot V2, which is nothing but V2 square, this will become, you can check that this will become L1 square theta 1 dot square plus L2 square theta 2 dot square plus 2 L1 L2 theta 1 dot theta 2 dot, then E theta 1 dot E theta 2. So this will be the expression for the velocity. And what is the E theta 1 dot E theta 2? E theta 2 is E theta 2 is in this direction. So if you allow me to draw a little bit in exaggerated manner, so this is the first mass, this is the second mass. Okay, E theta 2 in this direction, E theta 1 is perpendicular to this line. So this is M2, this is M1, and extended this. So E theta 2 is actually perpendicular to this line. So this angle, let us say phi. So this will be equal to cosine phi. E theta 1 dot E theta 2, this is nothing but cosine phi. And what is phi? What is phi?
Theta
This
2
ang-
minus theta.
Yeah, this angle is actually theta 1 minus theta 2. So this angle is theta 1 minus theta 2, or theta 2 minus theta 1. So since phi is equal to, so therefore this angle must be equal to this angle, because both of them, this is 90 degree to this line and that is 90 degree to the other line. So therefore this becomes cosine phi is nothing but cosine theta 1 minus theta 2. Okay, very simple vector result will give you this expression. Now we have everything now. So what is this is the kinetic energy I can find out in terms of all this stuff. Half v2 square you can just write down, and potential energy for the first mass, if you consider this as the reference point, the top point, then this becomes m1 g, this L1 and cosine theta 1. Okay, and for the second mass m2 g L1, the total one, the L1 cosine theta 1 plus L2 cosine theta 2. So this will be the potential energy. So what I have to do now, that I just substitute in here. So you see, you get equations only in terms of theta 1 dot, theta 2 dot, theta 1 and theta 2. T is not appearing there. So it was so simple. Just I get the value of the kinetic energy expression, which is a scalar equation. We don't have to bother about work with the vectors anymore. And most important is that we have got rid of our string tensions. String tensions are not appearing here anymore. So what we'll do now, once you get the value of this T1 and T2, so T1 and T2, this will be equal to half M1 L1 square theta 1 dot square plus half M2, then L1 square theta 1 dot square plus L2 square theta 2 dot square plus twice L1 L2 theta 1 theta 2 dot and cosine theta 1 minus theta 2. This is the 2 square, and this, so Lagrangian equation will be T, the kinetic energy, minus the potential energy plus M1 G L1 cosine theta 1 plus M2 G L1 cosine theta 1 plus L2 cosine theta 2, right? So this will be our Lagrangian. So then what we'll have to do, I'll get two equations. If you write down this Lagrangian, then you'll get two equations. First of all, what we'll have to do after that, you'll have to take the four derivatives. This is Q1, that means del L del Q1 I need, that means here Q1 is nothing but del L del theta. So take the partial derivative with respect to theta. This term will appear and this two terms will appear, theta 1. You calculate the value of del L del theta 2. So again, one contribution will come from here, another contribution will come from this expression. You'll calculate del L del theta 1 dot. Only the kinetic energy will contribute. So this term, and this term will appear. Then del L del theta 2 dot, you calculate. Okay. So once you get this equation, so once you derive those four expressions, then the equation of motion will be just like this. This will be del L del theta 1 dot minus del L del theta 1 equal to 0. There is no non-conservative force, and del dt of del L del theta 2 dot minus del L del theta 2 equal to 0. So this will be, these two equations will be our governing equations which we'll have to deal with. Understood the procedure?
Yes.
Well, I have not derived del L del theta 1 theta 2. This part I leave it to you. But I hope that you have understood the algorithm, the sequence of operation. Right? First, you find out the velocities. All the velocities will be required because we need the kinetic energy. So the kinetic energy expression we get. Okay. and the potential energy, we need the position. So we need to know the position and the velocity of the particles. So this much is required because in Newton's law, what we calculate is the acceleration. So we need to know the information of the position and velocity of the particles at the minimum. Then using this equation, we find out the acceleration. So once you have the initial velocity and initial configuration, and if you know the acceleration at any point, then you can find out the position and the velocity at any later point. So this is our the general procedure we follow in the mechanics. So we get the equation of motion and find out the position and the velocity at later instant. This process is clear. All of you.
Yes, sir.
Yes, sir.
Yes, sir.
Oh, good.
Yes, sir.
So this is one thing. I'll give you a small another small example where Newton's law may also be useful. But suppose this is one roller which is connected to the spring, and this roller. Suppose there is no slip here. So what will happen? If you just roll this roller, leave it, then it will oscillate, right? What is the degree of freedom of the system?
2.
2 degrees of freedom. If this is a pure rolling, suppose we consider this a pure rolling. What is the degree of freedom now?
1, sir.
1, sir.
Okay. So this is the mass, and suppose this is the radius. So how to write down the equation of motion then? So what I need is that I have suppose displaced the spring in this direction. Suppose well, in the anticlockwise direction. Suppose this is I and this is J. It's visible.
Visible, sir, visible.
Okay, so first of all, I'll have to, if you use Newton's law, then you will have to first draw the free body diagram and write down all the equations of motion. So if you draw the free body diagram, when this is rolled by an angle, let us say theta, so what will happen? Because this is pure rolling, so when it rotates by an angle theta in this direction, then this point actually advances by amount r theta, right? Isn't it? So
Yes, sir.
pure rolling means that if this point actually moves by an amount x, let us say in this direction, then it will roll by amount x by r magnitude, right? So this will roll. So what it means that this will happen provided it rolls in this direction. So this point will go to this point. So there's a rolling operation, and theta will be equal to x by r. So this amount of rolling will take place if this is a pure rolling condition. Okay, so when it has rolled by an amount theta in the anticlockwise direction, so this will move. So therefore, the force on this particular will be equal to, in this case, this will be k times r theta, the force acting on this direction, and here there will be this normal reaction and the friction force. Friction force will be arbitrary, we do not know because this no slip, so therefore this kind of static friction, there is no relative velocity, the friction force is actually an unknown force, and the normal reaction, and then we have, so this is only the free body diagram. Now what will be the equation of motion? Equation of motion, in that case, this will be, now equation of motion, in this case it will be m acceleration, this is equal to k times r theta, right? Acceleration is mass times acceleration is this one, and of course, sorry, r theta and minus f here, force. And
Yes, sir.
okay, it's a vector equation I write down, and suppose this is a, that means x double dot, and another one will be equal to, I'm sorry, this will be mg is acting, so n equal to n minus mg. Okay, so this the two equations, and I times theta double dot, this will be the net torque acting on this body, and this will be equal to nr. So this will be, what will be that? This will be on this one, this will be equal to minus f r, right? Isn't it? That's it?
Yes, sir.
Yes, sir.
Yeah. So this is what, and then A in this direction, A will be equal to r theta, because sorry, A is equal to r theta double dot, because x will be equal to r theta, r is constant, so therefore A will be A in this direction, the this part in this direction, this will be equal to A will be equal to minus r theta, because I have considered acceleration positive in this direction, and when it is rolling in the opposite, in the anti-clockwise direction, acceleration will be in the leftward direction, so therefore it will be minus r theta double dot. Okay. So this becomes actually m r theta double dot. This is equal to k r theta. Is this part clear? Clear to you?
Yes, sir.
Okay. And then see, f will be equal to, from here I'll get minus f, this is equal to I theta double dot by r, right? So what I'll do now, I'll do what I do, I'll substitute this equation into this equation, and I'll get then m r plus I by r theta double dot plus k r theta equal to 0, or let's say I plus m r square theta double dot plus k r square theta, this is equal to 0. So this will be our equation of motion. Now for that, actually what I needed, this information, of course this is not required, but well, this will check whether there will be slip or not, but anyway, assuming that this is actually very much rough surface, so this checking is not required, I still have to actually eliminate F, the friction force, which is unknown force here, okay, in Newton's method. But if you apply Lagrange, this equation is clear to you? All of you?
Yes, sir. Yes, sir.
Yes,
Okay.
sir.
Okay. So if you now want to derive the same equation of motion using Lagrange method, then what will have? Lagrange equal to 10 t minus u. Okay, and what is t? The kinetic energy, half mv square plus half I omega square. Okay, so this is the kinetic energy, and v is the velocity of the center of mass. That means the center of the disk. So therefore, this will be half m r square theta dot square and half I theta dot square. So this becomes half I plus mr square theta dot square. Potential energy is nothing but half k x square, which is nothing but r square theta square. So this will be equal to half I plus mr square theta dot square minus half k r square theta square, right? So the Lagrangian, then I'll have to consider del L del theta, which in this case is nothing but minus k r square theta, and del L del theta dot, which is equal to I plus mr square theta dot, right? Then the equation of motion ddt of del L del theta dot minus del L del theta, this is equal to 0. This will give you derivative I plus mr square theta double dot plus kr square theta equal to 0. So this is the same expression which we have got earlier using Newton's law, but see, the earlier method was you have to be very careful. You'll have to write down the equation of motion very carefully, and then you have to substitute, you have to eliminate the unknown quantities, unknown things. You'll get ultimately the equation of motion. But here this is so simple. Okay. So simple, that is, you only need the information of the kinetic energy and the potential energy, which is written in terms of the velocities. Velocities are very easy to find out, not as difficult as acceleration. So we get the velocity and position. So I can find out the Lagrangian, that means the difference between the kinetic energy and the potential energy. And using then and this very algorithmic process, I can derive the equation of motion. Have you understood this part?
Yes, sir.
Okay.
Yes, sir.
So now you see it is easy, but there is there is something which is of course missing in this particular formulation, is that the unknown reaction forces we have not found out. In mechanical engineering, of course, in design, we need to know the reaction forces sometimes. And in the design case, of course, we need to know, for example, the bearing, the resistance force, the reaction force at the bearing, the hinge. When we want to design the hinge, for example, the diameter of the roller in the hinge, then we need to know the force which is to be carried by the bearing. So we need to know for the design those reaction forces. For example, in this particular case, just to ensure that the rolling is taking place, we need to find out F, because we have to satisfy this condition that this has to be the magnitude of F needs to be less than or equal to mu s times n. So in order to ensure that, we need to find out F, and this F we cannot find out from this Lagrange technique. So that's why mechanical engineering, although this gives a very this Lagrangian methods is very shorthand method and very effective tool for deriving the equation of motion, but still we need to know the unknown reaction forces, because they will help us in designing the system. So that's why Newton's law, we do not actually, this is as important, we consider in mechanical engineering as important as this Lagrange equation. So we'll have to work with both of them. And secondly, I said that if you have the forces, the reaction forces or the constant forces only ideal. But in this case, actually the force is ideal because there is no slip. But if as soon as the slip takes place, then this method does not work, because our starting point, that is, we consider the constant to be ideal constant. The ideal constant, the ideal nature does not hold if there is a slip. There is a friction between the, there's a slip between the roller and the ground. Then, of course, this method will not work, and we'll have to revert back to Newton's laws, okay, using the Newton's equation. So I'll talk about this one later, and then quickly I go to the different kinds of vibrating systems. I'll give you an overview of the vibration problems, which normally in vibration engineer has to keep in mind. But this technique I want you to master, because the equation of motion can be derived very easily using this technique.
Our next class is started.
Yes. Okay.
Next
So I'll leave you now. So we are meeting again on Monday, next Monday, and next Wednesday we'll have the first tutorial again. Okay. So
Thank you, sir.
I'll leave you now.
Thank you.
Thank you, sir.
Thank you, sir.